In this video, we discuss learning outcome number 5 of lesson 7.2, which is about finding and interpreting a confidence interval for the population mean in the uncommon situation when the population standard deviation sigma is known. So here are our formulas. Say under certain conditions, the confidence interval for the population mean can be computed when the population standard deviation is known, and it would be computed using these formulas. Now, if you're wondering what those conditions are, those conditions are that the sampling distribution of the sample means needs to be approximately normal. So if the original population was a normal distribution, the sample means will also have a normal distribution. So that's appropriate, or these formulas are appropriate in that case. These formulas are also appropriate if the sample size is greater than 30, which means that a normal distribution is an appropriate approximation for that sampling distribution as well. So if one of those conditions holds, this is our confidence interval. It's just the sample mean minus the margin of error to the sample mean plus the margin of error. And this time, since we know the population standard deviation, we can compute our error this way. Rather than having a critical value of t, we've got a critical z-score, z sub alpha over 2. And we multiply by the population standard deviation, which happens to be known, and we divide by the square root of the sample size n. So here's an example. It says a simple random sample of 195 baby boys has a mean birth weight of 32.7 hectograms and a standard deviation of 6.6 hectograms. Assume the population standard deviation of the birth weights of baby boys is known to be 6.6 hectograms. Then we want to use a 95% confidence level to construct a confidence interval. Okay, first we need to check the requirements. Do we have a simple random sample? And yes, we were told that the sample was a simple random sample. And then we next need to check that the sampling distribution of the sample means is approximately normal. And since n is equal to 195, and that's definitely greater than 30, the distribution of sample means can be approximated by a normal distribution. So what we're about to do is just fine. So the requirements are met. Next thing I would do is state the given information. We were told that the sample mean is 32.7 hectograms. We were given the population standard deviation of 6.6 hectograms, and we were asked for a 99% confidence level. That's important because that's going to determine the critical z value. Next, we need to compute that critical z value. Now, there are lots of ways that we can do this, but first thing I would do is find the alpha value. When you have a 99% confidence level, you're looking for that 99% of common values of that sample mean x bar when you're looking at the sampling distribution of the sample means x bar. So we want 99% of those values in the middle. That means alpha is the complement of that, so that's 1%, but 1% in decimal form is 0.01. Now we've got 99% of the values in the middle. We want 1% of the values in the tails, but we're going to split that. So you're going to have half a percentage in one tail, and you're going to have 0.5% of the area in the other tail. So now we want to sketch a standard normal distribution with a middle area of 99% shaded. So you might have something that looks like this. Now, whenever I sketch this, I'm just drawing a bell curve, and I'm labeling that middle area with whatever confidence level is appropriate. So if we've got a 99% confidence level, that area under the curve is 0.99. That's that percentage, but in decimal form. And then we need to find the critical z value. So remember, the critical z value is the z value that separates this top 0.5% of the area from that bottom 99.5% of the area. So in decimal form, this critical z value is a z value that separates that 0.005 area to the right from that 0.995 area to the left. So 99.5% of the area to the left and 0.5% of the area to the right. Now at this point, you could find the area to the left as 0.995 and then look for 0.995 in the body of table A2 and find the z value that way. You can look in the bottom right-hand corner of table A2 and find this confidence level of 99%. It's one of the top 3 most common confidence levels. You can find the critical z values there, or you can use Excel. And you can use that norm S inverse function that we've used in other videos in order to find the z value. Any one of those would be fine. I'm just going to look it up in table A2 right now. Since our confidence level is 0.99, the critical value is this value right here. Z equals 2.575. Okay, so now that you've got your z value, we can compute the margin of error. The margin of error is that critical z value times that population standard deviation divided by the square root of the sample size, just plugging everything in, and then I'm estimating. Make sure you put that in your calculator correctly. So you can do this times this divided by this square root, or you can do this times, open parentheses, this fraction, close parentheses, and then hit equals. And you'll get an error of approximately 1.217. Now, if you enter this into your calculator incorrectly, you might get a different answer. So if you get a different number here, you might check your order of operations. Missing parentheses are often an issue when students are trying to enter this into their calculator. The student actually knows what they're supposed to do, that they have trouble getting the calculator to give them the answer because they're entering it wrong. Come see me if you need help with that. Just shoot me an email and we can talk about it, definitely. So now you've got your margin of error, and we already had that X bar was given to us. So now we can find the upper and lower limits of the confidence interval. So we have a sample mean of 32.7 hectograms, and we've got a margin of error of about 1.2 hectograms. So we subtract 1.2 from that 32.7 and we get this value. And then we add 1.2 to that 32.7 and we get approximately this value. And I think I will round to 1 decimal place rather than 2. Since we've got our upper and lower limits now, we can state our confidence interval. So the true value of that population mean, which represents the true mean weight of these baby boys, lies within this range of 31.5 hectograms to 33.9 hectograms. This was a 99% confidence interval. So we are 99% confident that the true value of the mean is in that range. Now you could write it in interval notation, or you can write it in this notation, X bar plus or minus the error. Now, if we're trying to interpret this, remember, all of this is based on that sampling distribution of the sample means. And that sampling distribution of the sample means is based on a particular sample size n. Because the way we construct it is we say, okay, let's create a sample of size 195. And then let's put all those babies back in and then create another sample of 195 babies. And then do that again, and do that again, and do that again. And every single time we do that, we compute a sample mean. And then we look at the distribution of those sample means. And that's what led to the inequalities that define our confidence intervals. So this information is based on that sample size. And this is how we can interpret that confidence interval. If confidence intervals were constructed in this way, for all such samples of size 195, the true population mean will fall within 99% of such confidence intervals. So of lots of different confidence intervals, 99 out of 100 of them, we're going to have that true population mean within that range. And that's fantastic. Or we can say it in this way. We can say we have 99% confidence that the mean, the true mean, the population mean, is between 31.5 hectograms and 33.9 hectograms. Okay, so sometimes students get confused at this point and they're like, when am I supposed to use the z-scores? When am I supposed to use the t-scores? That's what this last slide is about. You're trying to decide between the student t-distribution and the z, or standard normal distribution. If you don't know your population standard deviation, and most of the time we don't, you have to use the student t-distribution. Now you're using the student t-distribution when that population standard deviation is not known, but it's also required that the sample means are normally distributed or can be approximated by a normal distribution. So we know that that's true if the original population was normally distributed or if our sample size is larger than 30. So if the population was normally distributed and the sample or the sample size is larger than 30 or both, and we don't know the population standard deviation, use the student t distribution for your critical value. Now, if you know the population standard deviation and the original data set was normally distributed or our sample size is larger than 30, then we're going to use that normal distribution with the z-scores. In reality, that doesn't happen very often. And then lastly, if the population is not normally distributed and we have a very small sample, we can't use these methods. There is another method called the bootstrapping method covered in 7.4 that we're not going to cover in our class. There is a non-parametric method that you might be able to use in that case, but we're not studying those in our course. So you're either going to be in this case or this case, and we use this case whenever the standard deviation is not known. Use the t distribution. When the standard deviation is known, use the z distribution. But remember, in both cases, you need to check and make sure that you have reason to believe that those sample means are normally distributed, which means the sample size is large enough, greater than 30, or the original population is normally distributed.